Hi all, welcome to the class again. We were discussing Proton NMR spectroscopy. When we look at the instrumentation, the sample is placed in a sample tube and it is placed between two magnets. Generally for a 60 megahertz instrument, the magnetic field is 1.41 Tesla. It is 1.41 Tesla is stable at room temperature, but when you want to use higher magnetic fields, they are not stable at room temperature, so we will go for superconducting magnets. When we use superconducting magnets, they must be cooled down below room temperature. Generally, the superconducting magnets will be cooled by liquid helium, whose boiling point is minus 180 degrees centigrade. Because it is having such a low boiling point, it will be further cooled by liquid nitrogen. So inside chamber we will pour liquid helium, outside chamber we will pour liquid nitrogen. So liquid nitrogen plant we will set up when we buy the instrument. So every week we will fill the instrument liquid nitrogen chamber with liquid nitrogen, and every year we will fill liquid helium if something is evaporating from this. Now, what will happen? We apply a radio frequency RF waves. So there will be electric coils. We apply RF waves, RF energy to the compound. Then protons will absorb energy. They will undergo spin inversion, and when they do reverse this process, then energy will be emitted by the protons. That energy will be detected. So the emitted energy will be detected. Say for example, I'll write in this direction. The emitted energy will be given to a detector. So detector detects these signals and it will give signal to the computer. So computer generates a graph for us. So this is how NMR instrumentation works. Here the frequency of the instrument, I'm saying 60 megahertz, just 120, 100 or 200 or 300. It depends on the inbuilt magnetic field. So it is a fixed term. When we buy 60 megahertz instrument, so its magnetic field strength is 1.41 Tesla. That means we are buying a magnet of strength 1.41 Tesla. If you want 300 megahertz, we need to multiply 1.41 by 5 times. So something like this. The frequency of the instrument, it is based on the magnetic field which we are applying. Now we will discuss about equivalent and non-equivalent protons. What are equivalent protons? Protons in the same chemical environment they are called as equivalent protons. Protons in the same chemical environment are called as equivalent protons, and equivalent protons will give one signal. Equivalent protons will give one signal. For example, you take methane. All four protons are equivalent. So when we take the proton NMR spectrum of methane for these hydrogens, it will give only one signal. Why? because all the 4 protons are equivalent. We cannot differentiate any 2 protons. Similarly, ethane. See, these are having equivalent chemical environments. How do we define equivalent? If you have the same connectivity, the simplest shortcut is, if you have the same connectivity, then they are chemically equivalent. Say for example, this methyl group, it is bonded to another methyl. This methyl group, it is also bonded to another methyl. That means these 2 methyl groups are chemically equivalent. So that means this methyl is having 3 protons. Here also we have 3 protons. Altogether we have 6 protons, and these 6 protons are chemically equivalent, so they will give only one signal. Though we have 6 protons, they will give only one signal. Consider benzene. Benzene is also having 6 protons. But see, all these protons are having same chemical environment. That means the bonding nature around this carbon and this carbon, it is same, and it is bonded to 2 sp2 hybridized carbons. This is also again bonded to 2 sp2 hybridized carbons. So all the 6 carbons in the benzene are equivalent. So that means these protons are having equivalent chemical environments around these 6 protons. So they will also give one signal. Similarly, we can go for cyclohexane, where we have 2 protons on each carbon. They all have similar or same chemical environment, so they are all equivalent protons. They do give one signal. Take acetone. Acetone is again having 2 methyl groups, but look at the chemical environment. This methyl group is bonded to C double bond O carbon, carbonyl carbon. Again, this methyl group is also bonded to carbonyl carbon. That means these 2 methyl groups are having same connectivity. That means these two, the protons on these 2 carbons, they are equivalent protons. Because they are equivalent protons, they will give one signal. Now look at the some more examples for equivalent protons. Please take the notes. At the same time, if you have any doubts among these examples regarding whether they are chemically equivalent or not, please raise your question. These are all examples for chemically equivalent protons. So all these compounds will exhibit only one signal in their proton NMR spectrum. Now we will discuss about non-equivalent protons. Protons in distinct chemical environments or different chemical environments from one another are called chemically non-equivalent protons, and they give different absorption peaks. Even NMR is also an absorption spectroscopy, so I have written absorption peaks. Now we will look at some examples for chemically non-equivalent protons. Take N-propane. When we look at N-propane, the 2 methyl groups, they are chemically equivalent. This methyl group is bonded to an sp3 hybridized CH2 group, sp2 hybridized, or we can simply say methylene group. Even this methyl is also bonded to a methylene group. So that means the chemical bonding around these 2 methyl groups, it is same. So these 2 are chemically equivalent. Whereas this CH2 group, it is chemically non-equivalent from these 2 methyl groups. It is CH2, right? So So the number of protons itself, it is different. Here we have 3 protons, here we have only 2 protons. That means these 2 protons are chemically different from other protons. So how many signals we expect here? We expect 2 signals. One signal for the 2 methyl groups and one signal for the methylene group. So we expect 2 signals from this compound. Similarly, we will take methyl acetate. Methyl acetate. Of course, we have 2 methyl groups, CH3, CH3. Now it is the point to look whether they are chemically equivalent or non-equivalent. Right. This methyl group is bonded to a carbonyl carbon, whereas this methyl group is bonded to a oxygen. Though 3 hydrogens are present on each carbon, but these 2 methyl groups are chemically non-equivalent because this methyl group is attached to a carbonyl carbon, whereas this methyl group is attached to an oxygen. So these 2 methyl groups will give 2 signals, one signal for this methyl, one signal for this methyl. So here also we will get 2 signals. We will take even some more simple examples. Ethyl chloroethane. Of course, the number of protons around this methyl and methylene group are different. So we can simply say that these 2 are chemically non-equivalent. This carbon is bonded to a methyl group and a chlorine, whereas this methyl group, it is bonded to a methylene carbon. So these 2 methyl and methylene carbons, they are chemically non-equivalent. So they will give 2 signals, one signal for CH3, one signal for CH2. Now we will go to some complex example. Ethyl acetate. Ethyl acetate. Here we have 2 methyl groups and one methylene carbon. Now, this methyl group is bonded to a carbonyl carbon, whereas this methyl group is bonded to a methylene carbon. That means it is chemically different. This is also chemically different. That means these 2 methyl groups are chemically non-equivalent. And when we look at this methylene, yes, methylene carbon is bonded to oxygen and methyl. So it is also chemically non-equivalent. When we have different protons, here 3 protons, here 2 protons, we can easily say these 2 are chemically non-equivalent. So here we will get different signals for this methyl, methylene and methyl. So altogether we will get 3 signals here. We will get 3 signals here. For example, look at this molecule. How many signals we will get? Can anyone answer this? Tolin, how many signals we can get? Dimethyl salicylate. How many signals we can expect for this molecule? Look at this example. This is a tertiary butyl carbon. These 3 methyl groups, they are bonded to a tertiary carbon. So that means the chemical environment among these 3 methyl groups, it is same. So these 3 methyl groups will give one signal. These 3 methyl groups will give one signal. Whereas this methyl group, it is bonded to an oxygen. So it is in a chemically different environment compared to these 3 methyl groups. So it will give another signal. So altogether we will get 2 signals. Here also this methyl group and aromatic protons, all aromatic protons will give 1 signal in a low resolution spectrum. This methyl group will give 1 signal. So altogether we will get 2 signals. Here also these 2 methylene groups will give 1 signal. These 2 methyl groups will give 1 signal. So a total of 2 signals will be observed in this compound. We will discuss position of proton NMR signals. The chemical shift values of protons are what we can say delta values. The delta values of different protons, they are affected by electronegativity of the attached atoms, then hybridization of the attached carbon, finally anisotropic effect. Nothing but shielding. So these 3 factors will influence the chemical shift values. Now for simplicity, before going to the exact values of exact delta values for different compounds, first we will look at the order of delta values for different protons. In this compound it is nitropropane. When we have more electronegative atom, then the delta value will be higher for this. It tries to withdraw electrons, so it decreases the electron density around this methylene carbon. So it will have low shielding, or the resultant is very high, resultant effective magnetic field is high. So the signal will be observed at high frequency among other protons. Now when we look at the inductive effect, nitro directly decreases the electron density here, then here, then here. So using electronegativity and inductive effect, we can easily identify which protons will have higher delta value, next higher, and the lowest. This methyl group, it is surrounded by large electron density compared to other methylene carbon. So its delta value will be very, very low. It is at high shielded region. Similarly, we will take ethyl acetate. In ethyl acetate, the carbon which is attached to oxygen electronegativity is 3.5. So the protons on a carbon which is directly attached to oxygen will also observed at a delta value of around 3 to 4 ppm. So here the highest delta value is observed for protons which are on a carbon attached to oxygen. Among this methyl group and this methyl group, it is attached to sp3 hybridized carbon, whereas this is attached to sp2 hybridized carbon. sp2, as we say, percentage of s character is proportional to electronegativity. This is more electronegative carbon than this. So this methyl group is on a more electronegative carbon, but this methyl group is not on a more electronegative carbon. So that is why they will withdraw electrons from this, so they will appear at a higher delta value compared to this. So here the protons on a carbon which are directly attached to oxygen, they will appear at a higher delta value than the methyl carbon which is attached to carbonyl carbon, than the protons on this methyl carbon. Now we will look at a different example. methyl propionate. When we look at the methyl propionate, the same concept can be applied here. So the highest delta value can be observed for these protons because this carbon is directly attached to more electronegative oxygen. So this is A. The next highest delta value will be this methylene carbon because it is attached to carbonyl carbon. So it is B. And it is attached to an sp3 hybridized carbon. So it will be observed at a low delta value. Similarly, in this molecule 1,1,2 trichloroethane, this carbon is attached to two chlorines. This carbon is attached to only one chlorine. Here the electronegativity differences can be added. Electronegativity can be added. So when we have two chlorines, it feels very high electronegativity. So these two chlorines will withdraw a high electron density from this carbon. So it will be observed at a large value. Whereas this carbon, it is having only one more electronegative chlorine. So it will be observed at a low delta value among these two. Now we will look at toluene. Toluene is having a methyl carbon and 5 protons on benzene. Methyl carbon, the protons on methyl, they will give a low delta value, whereas aromatic protons, they will be observed at a large delta value. So that is due to the anisotropic effect that I will discuss later. But here aromatic protons will be observed at a larger delta value. Non-aromatic protons will be observed at a lower delta value. Now we will look at the alcohol, ethyl alcohol. Since oxygen is directly attached to more electronegative atom, it will be observed at very high delta value, then this fellow and then this fellow. I'll give you one example for practice. So you just tell me which protons will be observed at high delta value, which protons will be observed at less delta value. Delta value ranges from 0, 0 is for TMS, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Generally alkane protons, they will be observed between 0 to 2. So generally 1 to 2 ppm. Alkane protons will be observed between 1 to 2 ppm. Then between 2 to 3 ppm, we will observe a variety of compounds. For example, benzylic protons or allylic protons are protons and a carbon which is also having nitrogen, Triple bond proton directly attached to sp3 hybridized carbon. It is also observed between 2 to 3. It is an exceptional case. I will discuss it later. And acetone protons, that means protons on a carbon which is next to carbonyl carbon, they are also observed between a delta of 2 to 3 ppm. So benzylic, allylic, protons on a carbon which are attached to nitrogen, then proton on sp3 hybridized carbon, then protons adjacent to a carbonyl carbon. They all will be observed between 2 to 3 ppm. Now between 3 to 5 ppm, the protons on a carbon which are attached to fluorine, because fluorine electronegativity is 4, so these protons are generally observed from 4 to 4.5. If we have chlorine electronegativity is 3.3, so they will be observed between 3.3 to 3.6 ppm. If we have bromine electronegativity is 2.8, so they will be generally appeared between 2.2 to 2.7. If it is iodine electronegativity is 2.5, they are generally appeared between 1.8 to 2.3. If it is oxygen electronegativity is 3.5, so they are generally appeared between 3.5 to 4. For precise, I am writing 3.8. If it is a nitro group or any strong withdrawing group like nitrile, then they also appear around 4 ppm. Now between 4.5 to 6.5, vinylic protons, 4.5 to 6.5 ppm, vinylic protons will be observed. That means protons on a double bond. Between 7 to 8, aromatic protons will be observed. Aromatic protons between 7 to 8 ppm. Now the aldehyde proton is observed between 9 to 10. Aldehyde proton is observed between 9 to 10. Carboxylic acid proton is observed between 10 to 12. Aldehyde proton is observed between 9 to 10. Carboxylic acid proton is observed between 10 to 12. Phenolic proton is observed between 4 to 7. Phenolic proton is observed between 4 to 7 ppm. Apart from this, we also have protons on alcohol or protons on nitrogen. These are called as exchangeable protons. So we can easily exchange these protons. So they are having a very large range of delta values. Oxygen protons are generally observed between 1 to 8 ppm. Sometimes we may not observe also. Protons and nitrogen are observed between 1 to 5 ppm. It is due to their electronegativity differences. Oxygen is more electronegative, nitrogen is less electronegative. These are called exchangeable protons. These are called exchangeable protons. These sometimes we may observe, sometimes we may not observe these protons.